All right, hello, my name is Mr. Anderson. Today's first video is on bisectors. Specifically in this video, we're going to be talking about perpendicular bisectors. You got a line that's both perpendicular and it bisects another segment. And we're going to be talking about angle bisectors. Some line or ray that cuts an angle in half. Going to talk about a couple of their properties, talk about constructions of them, and maybe do a couple of proofs. All right, so first off is perpendicular bisectors. You guys should know how to do a construction of a perpendicular bisector, but I'm going to run through that really quick because one thing that you might not have learned when you learned that construction is why it works. So, one moment. Okay, so there's a little bit of a delay on this video, but not too bad. If you're going to construct an angle bisector, again, you take your compass, set it to something over half of this segment. Doesn't matter if it's way over half or a little over half. Just over half the length of the segment so that you can make a couple marks. Some people like making big marks all the way across. Some people just like making a little mark there, a little mark there. Doesn't matter as long as when you do it from the other side, they intersect. Now this one I missed, so I can just fix that. I'll come back to this side and I'll finish that up. Now, the important thing when making a perpendicular bisector for it to work is when you make these arcs from the one side, you definitely do not change the size of your compass. Use the exact same size, the exact same opening of your compass from the other side. The reason that's important is when you keep those distances the same, that intersection point and that intersection point land right on the perpendicular bisector. That's why when you connect them up, it makes a 90-degree angle and cuts a segment in half. Turns out that in a perpendicular bisector, any point on that perpendicular bisector is the exact same distance from both sides of the endpoint. So when I used my compass, I created a segment right here and a segment right here that were the same length, which meant that point had to land on the perpendicular bisector. Same thing over here. That distance and that distance are the same length, so that had to land on the perpendicular bisector. That fact actually makes it nice for us to, here, I'll show you. If I wanted to make a perpendicular bisector on the edge of a paper, like that, taking my compass and putting it over half the length, I can definitely make an intersection here and have a point land at the perpendicular bisector. But I can't make one down here because I run out of paper. And one point is not enough. I wouldn't know, do I land it up here? Do I put it there? Right? It would be here-ish, but then I'm eyeballing this point. I really don't know for sure. So if I wanted a second point so I can actually create that line, all I need to do is change my size of my compass and just find another point. That distance and that distance are the same. So they will also land on the perpendicular bisector. And I can do a perpendicular bisector by matching this point up and this point up because they'll land on the perpendicular bisector. Matching those up, goes down. Yep, that looks perpendicular. That looks like it bisects the segment. All right, so that's going to be one of the big facts for perpendicular bisectors. The distance from an endpoint to the perpendicular bisector is the same, or sorry, the distance from an endpoint to a point on the perpendicular bisector is the same from both endpoints, right? Just like that one and that one, those are going to be the same. I've got a proof of what we had just mentioned, that if you're given that M is a perpendicular bisector, any point on it is equidistant from A and B. If you would like to have a little bit of practice on proofs, I would definitely recommend giving this one a try. I'm going to run through it really quickly because proofs are something we should be getting a little bit better at, but it would still be a good thing to go over. So first off, it's giving me a bunch of information here. A diagram would probably be a helpful thing. So I'm going to make a diagram here. Let's see here. We got given, looks like we've got some segment AB. We're given that M is a perpendicular bisector. So here's line M. And we know it's both perpendicular and a bisector. And we want to prove any point on M is equidistant from A and B. That's what we want to prove. So I just need to give some point. Let's put some point here. Let's call that one C, so it's got a name. Maybe we'll just call this one M for midpoint. And we want to prove that this distance from A to C is the same as from B to C. So we got to list a few things, right? So what do I know about this picture? First, I know M is the perpendicular bisector. I'm gonna just abbreviate perpendicular bisector of AB. And again, of course, the big thing about a proof is anytime you say something, you got to say why you know it's true. Why do I know that's true? Well, that was given. Because I know M is a perpendicular bisector, that means I definitely know that AM is congruent to BM. And I know that's true because that's what a bisector does. It cuts it in half. So that's by definition of bisect. And I definitely know that angle AMC is equal to angle BMC, which is equal to 90 degrees. I know those are all equal to 90 because that's what perpendicular means. Definition of perpendicular. All right. I wanted to show that these two dotted lines were congruent, so it'd be really nice if I could show that those triangles are congruent to each other. I just need one more part, and it's, hopefully you're seeing it right here. CM is congruent to CM. It seems silly to list that one, but if I want to show the triangles are congruent, I'm going to need the side angle side, which means I need to list all those parts, right? Proofs are very particular, list everything you know and why you know it. This one's always a funny one. CM is equal to CM. Well, of course it is. That seems silly. So the way I write it is, well, the way a lot of people write it would be the reflexive property. The reflexive property just says that anything is equal to itself. 5 is equal to 5, 8 is equal to 8. That's true for most things, right? All right. Now I've listed a side, I've listed an angle, I've listed a side. I think I can list those triangles are congruent, making sure I list them in the right order. Triangle AMC is congruent to triangle BMC. How do I know that's true? By the side angle side theorem, right? And finally, since the triangles are congruent, all of their parts are congruent. So I know AC is congruent to BC. By that fun little shortcut, CPCTC. Corresponding parts of congruent triangles are congruent. A few things to note, because I am not all of your teachers. This is a particular type of proof that's very similar to something called a two-column proof, where you put things you know on one side of the column and reasons you know it on the other side. So that's a form of a two-column proof in case that's new to you. If you want something fun and silly, I gave my students a fun and really kind of goofy way to remember CPCTC. It does stand for congruent parts of congruent triangle, corresponding parts of congruent triangles are congruent. I played Battleship as a kid, and the PT boat was one of the smallest boats, the patrol boat. And so I always remembered a PT boat lost in the seas. It was fun. All right. Anyway, let's move on. This is a proof I was going to work through. Point C is equidistant from points A and B. If that's true, then point C is on the perpendicular bisector. That's showing it the other way around. It's saying, hey, if you happen to know that there's some point C here, and you know that this length is equal to this length, then you know that the line C is on is the perpendicular bisector. Right, I'm going to leave that as a proof for you. It'd be a good practice. I do not want to spend a lot of time going over this one because I want to keep these videos short and sweet. All right, so big important thing. A point is on the perpendicular bisector of a segment if and only if that point is equidistant from the segment's endpoints. That little IFF, if you didn't already know that, that means if and only if. And what this statement is really getting to is it's saying that it works both ways. If you know you have a point that's equidistant from two endpoints of a segment, then you know that this thing here is a perpendicular bisector. Or the other way around, if you know you have a perpendicular bisector, then you know that any point on that perpendicular bisector is equidistant from the endpoints. Right? If and only if statements just means it works both directions. All right. Angle bisectors. Here's the new one for you. You guys hopefully already know what an angle bisector is, right? It's something that cuts an angle in half. But Turns out that if we have an angle bisector, it's going to be equidistant from the sides of the angle. Again, I normally work through a proof for this type of thing. This would be a good thing for us to do in class, but I don't want to use a video doing it because I want to be able to answer questions. So I'm just going to give the idea for what this is talking about. If we have some angle ket, okay, ET, and we know that I is on the perpendicular bisector. Let's call I, let's put it way up there. And that's an angle bisector. We know I is on the angle bisector. Then we know that point I is equidistant from the sides of the angle. We know that this distance down to that line and this distance, see if I can make it hit there, right about there, to that line, we know those distances are going to be equal. You'll notice, of course, when we measure distance from a point to a line, it's a perpendicular distance. That's why I landed it here and there. If you have a point on the angle bisector, we're going to have a perpendicular distance be equal. So this segment and that segment will be equal. That fact is going to help us to be able to construct an angle bisector. And that's what I'm going to show you next. This proof would be a good proof to walk through. I might do that during our live session in class. All right. Constructing an angle bisector. Well, first important information, a point is on the angle bisector of a segment if and only if that point is equidistant from the angle sides. Again, that just means as long as you know the point is equidistant from the angle sides, it's on the bisector, or the other way around. If a point's on the bisector, it's equidistant from the angle sides. All right, that allows us to learn how to construct an angle bisector. So that'll be next. All right, so constructing an angle bisector. If you want to construct an angle bisector, we're actually going to use a property of quadrilaterals we haven't learned yet, but I'm going to talk to you about that. So first off, here's my angle. I want to cut it exactly in half. First step to constructing an angle bisector is taking your compass and making some arc over that angle. Any old arc, it doesn't matter how big. Next, I'm going to take my compass again. I like making my compass a little bit bigger because it's going to make my drawing a little bit more accurate. Put the point to the compass down here, draw an arc outside of the angle over there, and then come around here and make the same size arc right there. Wherever that intersection point lands, that is going to be right exactly on your angle bisector. So I take my straight edge, line them up. This angle and that angle are going to be the same length, angle bisector. The reason it works is essentially I constructed a figure where this side and that side are equal, and this side and that side are equal. That type of thing is called a kite, and turns out that when you connect these two vertices of a kite, it's going to cut the angle in half. So I used that fact to help me create an angle bisector. Now it does still follow the properties of angle bisectors, of course. If I drop this straight down to a 90-degree angle, and I drop that straight down to a 90-degree angle, have to extend that line a bit to see it. That's just a sketch, of course, not an actual construction. But if we measured this length and we measured that length, they would be equal. That's a property of angle bisectors. With angle bisectors, we could then actually construct more angles than what we currently know. Like right now, we know how to construct a 90-degree angle by doing a perpendicular bisector. But we can actually now make a 45-degree angle by first making a 90 and then bisecting it in half. In fact, we could even make a 22.5-degree angle by taking that 45 and cutting it in half again. Or cutting it in half again, I could make an 11.25-degree angle, right? There's all sorts of new angles this construction helps me make. Another type of angle we already know is a 60-degree angle. We can make that by making an equilateral triangle. Since we can make a 60, we can also make a 30-degree angle, which means we can make a 15-degree angle, which means we can make a 7.5-degree angle just by repeatedly cutting our angle in half. All right. That was our lesson on angle bisectors and perpendicular bisectors. The next lesson will be on actually centers of a triangle. There are more than one center. It's kind of cool. I'll see you then.